So I want to now describe the kind of differential equation that we're going to use phase lines to analyze. Now, remember, for first-order differential equations, they can all be written like this, right? And then we said, okay, well, if you can write it as, a function of x only times a function of t only, then we say it's separable, right? So it's always x prime equals a function of x and t, but if you can write the right-hand side as function of x times function of t, then it's separable, and you can use separation of variables to solve. Possibly getting stuck because integration is hard, but that's the only thing that can prevent you from solving once you have separated. Now I'm going to say, well, okay, if you can write it like this, if the right-hand side is a function of x alone, and there's no explicit time dependence in the right-hand side, then we say that the differential equation is autonomous. So an autonomous differential equation is one that can be written like x prime equals and then stuff involving x. So for example, x prime equals 3x plus the cosine of x squared. That's a really gross one, but that's autonomous. There's no t's. As soon as I introduce a t, like plus t, or multiply the whole thing by e to the t or something like that, then suddenly it's no longer autonomous. Now, notice that I'm not saying there's no time dependence. There's time dependence because these are functions of t, right? X is x of t. It's x of t. So the right-hand side still depends on time. I'm just saying it does not explicitly depend on time. It only depends on time via x, through x's dependence on time. So that's what's meant by autonomous differential equation. And the significance of this is that if you look at a phase line, so this is like the x-axis, so the different x of t values are taken along this line. If you look at the phase line, then for an autonomous differential equation, like x prime equals g of x, knowing where you are on the phase line tells you exactly where you're going to go next. So if you are like here, at some specific point, x naught, or let me give it a number. Let's say you're here at x equals 17, and that's your current location. Then, if the differential equation that governs your evolution in time is autonomous, then you know exactly where you're going to go next, just from knowing where you are. Why? Because your x prime, if x is 17, then x prime is whatever is g of 17. So maybe that's, let's say it equals 23. Then that tells you your rate of change in time, dx dt, is 23, meaning you're going to increase your x value by 23 units of x per unit of t. So you're going to move to the right. On the other hand, if maybe you got negative 23 here, then you would move to the left. So this is what's special about autonomous differential equations, is that where you are on the phase line determines completely where you're going to move next. And this is, I'm talking as though time is discrete, like from one moment to from one moment to the next, but of course it's more continuous. It's really where you are on the phase line determines instantaneously your rate of change of x. This wouldn't happen if the differential equation were not autonomous, right? If you had explicit t dependence here, then I wouldn't know where I'm going to go. I would also have to know what time it is. Okay, so for autonomous differential equations, we're going to be able to get a lot of we're going to be able to pack a lot of information into a phase line diagram.